Before soy became the global symbol of protein, another crop quietly fed people, animals, and soil at the same time. It matched soy in protein, fixed its own nitrogen, and grew without chemicals or GMOs. Then it vanished from fields. This is the story of lupin and why it was replaced. Long before soy dominated global agriculture, lupin was already established as a high-protein crop across Europe, North Africa, and the Mediterranean. Farmers didn't grow it as an experiment or novelty. They relied on it. Lupin seeds regularly reach protein levels comparable to modern soy, making it valuable for both human food and animal feed. In mixed farms, lupin filled a role that today would require fertilizers, supplements, and imported feed. At the time, none of that existed. The crop worked within the limits of the land itself, not against them. Unlike soy, lupin never depended on an industrial system to function. It fixed nitrogen naturally through its roots, enriching soil instead of depleting it. Farmers didn't need synthetic fertilizer to push yields because the plant evolved to cooperate with poor soils. In rotation systems, lupin improved the field for the next crop while producing protein at the same time. This dual role, food and soil repair, made it strategically important in low-input agriculture. Lupin was not optimized for factories. It was optimized for survival. Lupin thrived where soy struggled. Cold springs, acidic soils, marginal land, these were not barriers but advantages. In northern Europe and mountainous regions, lupin produced reliable harvests without irrigation or chemicals. This resilience mattered in pre-industrial societies, where crop failure meant hunger. Farmers valued plants that could tolerate mistakes, weather swings, and neglect. Lupin was one of them. Its success was not measured in maximum yield, but in dependable protein when conditions were uncertain. If lupin was so useful, the obvious question follows: why is soy everywhere and lupin almost nowhere? The answer is not nutritional, it is systemic. Lupin carried traits that worked well for traditional farming, but poorly for industrial agriculture. The plant did not fit neatly into large-scale monoculture models. It required local knowledge, crop rotation, and post-harvest processing. These were features, not flaws, but they made lupin inconvenient for a system built on uniformity and speed. Protein was never lupin's weakness. The real problem was bitterness. Traditional lupin varieties contain natural alkaloids that make the seeds unpleasant unless treated. For centuries, communities soaked and processed lupin using simple methods to remove bitterness. This knowledge was widespread but local. Industrial food systems, however, favor crops that require minimal preparation and centralized processing. Soy fit that model perfectly. Lupin did not. Convenience, not nutrition, became the deciding factor. As agriculture industrialized, priorities shifted. Crops were selected not for resilience or soil health, but for scalability, transport, and compatibility with chemical inputs. Soy responded well to fertilizers, pesticides, and genetic standardization. Lupin did not need those inputs, and that became a disadvantage. Systems built around selling chemicals had little incentive to promote a plant that reduced dependency on them. Slowly, lupin disappeared from rotations, markets, and memory, even though nothing about the crop itself had failed. When lupin vanished from fields, something else vanished with it: agricultural memory. Knowledge of soaking, fermenting, and using lupin for food faded within a generation. What remained was the assumption that soy had always been the superior protein crop. This assumption was never tested against history. It was inherited. Modern farmers rarely question why certain crops dominate, only how to optimize them. Lupin became invisible not because it was inferior, but because it no longer fit the dominant story of progress. Today, lupin's original strengths look less like relics and more like warnings ignored. A protein crop that fixes nitrogen, tolerates poor soil, and grows without synthetic inputs challenges the logic of modern farming. It exposes how dependent food systems have become on external energy and chemicals. Lupin represents a different agricultural logic, one based on cooperation with ecosystems rather than control. That logic was set aside, not disproven. Lupin was not replaced because it failed. It was replaced because agriculture changed its goals. The system no longer asked which crop could feed people sustainably. It asked which crop could scale fastest, ship cheapest, and integrate into industrial supply chains. Soy answered that question. Lupin answered a different one. Now, as soil degrades and inputs grow expensive, the old question returns. And with it, the forgotten crop that once answered it. For centuries, Lupin was not just animal feed. It was human food. In the Mediterranean, soaked and cooked lupin seeds were eaten daily, sold in markets, and consumed during times of scarcity. Its protein density made it valuable when meat was rare or expensive. Unlike soy, lupin entered diets long before industrial processing existed. People adapted to the plant, not the other way around. Food systems were local, slow, and shaped by necessity, not efficiency metrics. Traditional lupin preparation required time, water, and patience. Seeds were soaked, rinsed repeatedly, and sometimes fermented to remove bitterness. This process was simple but incompatible with industrial food timelines. Modern systems reward crops that can be crushed, extracted, and standardized quickly. Soy fits conveyor belts, refineries, and global shipping schedules. Lupin fits kitchens, villages, and seasonal rhythms. When speed became more valuable than resilience, lupin lost its place. Protein comparisons rarely tell the full story. Lupin's amino acid profile makes it highly digestible and useful for human nutrition. While soy dominates headlines, lupin quietly matches it in functional protein applications, especially when processed traditionally. In pre-industrial diets, protein was judged by how it sustained labor and health, not by lab numbers alone. Lupin earned its reputation over centuries of use, not marketing campaigns or subsidies. Modern farming treats soil fertility as an input problem. Fertilizer replaces what crops remove. Lupin followed a different logic. By fixing atmospheric nitrogen, it improved soil naturally, benefiting the crops that followed. Farmers didn't need to calculate nutrient deficits. The system corrected itself. This made lupin invaluable in rotations, especially where manure was scarce. Soil improvement was not a goal. It was a side effect of growing food correctly. Lupin thrives in diversity, not isolation. It performs best in rotations, mixed systems, and small-scale fields. Industrial agriculture favors monocultures because they simplify machinery, logistics, and chemical application. Lupin complicated those systems. It refused to behave like a uniform commodity. That resistance made it unattractive, not inefficient. In a system optimized for sameness, crops that support diversity are quietly pushed aside. Soy's rise is often framed as progress, higher yields, global distribution, modern efficiency. But this narrative hides trade-offs. Dependence on fertilizers, pesticides, and fuel increased alongside production. Lupin represented a path not taken, one where protein production remained tied to ecological balance. The disappearance of lupin wasn't inevitable. It was a choice. And like many choices framed as progress, its costs were deferred, not eliminated. Cheap fossil fuels and synthetic nitrogen reshaped agriculture. Suddenly, crops no longer needed to cooperate with soil. They could be forced. Soy thrived under this model, responding aggressively to inputs. Lupin didn't need them. And in an economy built around selling solutions to problems crops once solved naturally, a plant that reduced problems had little place. The market rewarded dependency, not independence. Those old limits are returning. Fertilizer prices rise, soil erosion accelerates, climate instability increases crop risk. Systems built on constant inputs begin to strain. In this context, lupin's forgotten traits look less outdated and more strategic. A protein crop that feeds people while repairing soil challenges assumptions about efficiency. It suggests that modern agriculture may have optimized the wrong variables for too long. Today, lupin quietly reappears in research plots and niche farms. Plant breeders focus on low alkaloid varieties. Farmers test it as a cover crop, protein source, and soil restorer. None of this is driven by nostalgia. It is driven by necessity. Lupin is not a miracle. it is a reminder. When conditions change, forgotten crops often outperform optimized ones. The real question is no longer why lupin disappeared. It is why it stayed forgotten for so long. Agriculture remembers what the system rewards. For decades, resilience had no price. Now it does. As protein demand rises and inputs grow fragile, Lupin challenges the assumption that soy has no alternative. It never did. We simply stopped asking the right questions. Comparing lupin and soy only by protein numbers misses the real difference. Soy performs best inside a system built on fertilizer, pesticides, fuel, and global logistics. Lupin performs inside a system built on rotation, soil biology, and low external inputs. One crop depends on constant intervention. The other reduces the need for it. From a systems perspective, lupin produces protein while lowering risk. Soy produces protein while increasing dependency. Modern yields hide hidden costs. Every ton of soy protein carries embedded fertilizer, energy, and chemical inputs. These costs are rarely visible at the field level because they are externalized. Lupin shifts those costs back into biology. Nitrogen fixation replaces fertilizer. Rotation replaces pesticides. Time replaces force. What appears less efficient on paper often proves more stable over decades. Lupin trades short-term optimization for long-term reliability. Agriculture scaled faster than its logic evolved. Decisions began serving supply chains rather than ecosystems. Soy scaled cleanly across continents with predictable behavior under chemicals. Lupin scaled unevenly, responding to soil, climate, and management. This variability discouraged investment. Uniformity became more valuable than resilience. The crop that behaved like a machine was favored over the one that behaved like a living organism. Lupin never aimed to maximize yield under perfect conditions. It aimed to guarantee protein under imperfect ones. In traditional systems, that difference mattered. Crop failure was catastrophic. Reliability was survival. Modern agriculture reversed the priority. Maximum yield replaced minimum failure. Soy fits that philosophy. Lupin does not. Yet as climate volatility increases, the value of guaranteed output rises again. Protein security begins to matter more than record harvests. Climate instability punishes fragile systems. Droughts, late frosts, and erratic seasons expose the limits of monocultures. Lupin's tolerance to cold, poor soils and irregular rainfall makes it strategically relevant again. Its strength was never abundance in ideal years. It was consistency across bad ones. In a warming, destabilized climate, crops designed for extremes quietly outperform those designed for averages. Today's lupin is not frozen in history. Low alkaloid varieties reduce bitterness. Breeding improves uniformity without destroying resilience. Farmers no longer need to rediscover lost techniques from scratch. Lupin adapts without losing its core advantage, protein production without chemical dependence. This evolution weakens the argument that lupin belongs only to the past. It belongs to a future shaped by constraint, not abundance. Despite its advantages, lupin faces structural resistance. Infrastructure favors soy. Processing facilities, subsidies, and research funding reinforce existing crops. Lupin competes not against soy plants, but against soy systems. Changing crops requires changing incentives. Until resilience carries economic value, alternatives remain niche. Lupin's slow return reveals how difficult it is for agriculture to correct course once momentum builds. Lupin reappears first where failure is costly and margins are thin. Small farms, cold regions, and low-input systems test it quietly. These farmers value crops that forgive mistakes. They measure success in stability, not volume. For them, lupin is not an experiment. It is insurance. History often returns through the margins before it reaches the center. Global protein demand continues to rise, but the assumptions behind its production are changing. Cheap inputs are no longer guaranteed. Soil degradation is no longer abstract. In this context, Lupin challenges the idea that soy is inevitable. It proves that high-protein crops can exist outside chemical dependence. The question is no longer whether lupin works. It is whether systems are willing to adapt. Lupin was not replaced because it lost value. It was replaced because value was redefined. Agriculture chose speed over resilience, uniformity over adaptability, scale over security. Lupin answered an older definition of success. Now that definition returns. Replacement, it turns out, was temporary. The crop waited. The system changed. Lupin did not vanish because farmers rejected it. It vanished because systems stopped supporting it. Crop choices follow incentives, infrastructure, and policy more than agronomy. When those forces aligned around soy, alternatives were sidelined. Replacement was not a scientific conclusion. It was an economic decision. Once made, it reshaped research, markets, and memory. Crops that fell outside the new logic quietly disappeared, regardless of their actual performance in the field. Forgetting a crop carries consequences. When diversity narrows, vulnerability increases. Protein systems concentrated around a single crop inherit that crop's weaknesses. Lupin once provided redundancy. It acted as a backup protein, adapted to different soils and climates. Removing it reduced options. Modern agriculture gained efficiency but lost flexibility. That trade-off remained invisible as long as conditions stayed stable. Instability reveals what forgetting costs. Soy is no longer just a crop. It is an entire system of fertilizers, genetics, transport, processing, and finance. Challenging soy means challenging that system. Lupin threatens it not by outperforming soy in yield, but by exposing its dependence. A protein crop that functions without chemicals questions why chemicals became necessary at all. That question is uncomfortable. Systems resist questions that undermine their foundation. This story matters because conditions have changed. Energy is no longer cheap. Soil is no longer resilient by default. Climate is no longer predictable. Crops designed for abundance under control struggle under volatility. Lupin was designed for uncertainty. It never assumed perfect conditions. It assumed limits. Agriculture is rediscovering those limits. Forgotten crops often return not as nostalgia, but as solutions. Lupin will not replace soy overnight. It will not solve every problem. That expectation belongs to industrial thinking. Lupin's value lies elsewhere. It diversifies protein sources. It reduces input dependency. It restores options. Progress in resilient systems is incremental, not revolutionary. Lupin does not promise abundance. It promises continuity. In unstable systems, continuity becomes the most valuable resource. The real competition is not Lupin versus soy. It is dependency versus resilience. One model assumes endless inputs and control. The other assumes limits and adaptation. Lupin belongs to the second model. It competes with soy only because both produce protein. Beyond that, they answer different questions. Modern agriculture favored one question for decades. Now another question demands attention. When Lupin was replaced, protein was not the only thing lost. Knowledge disappeared. Rotations simplified. Soil biology weakened. Farming became narrower. Replacement often removes invisible functions first. Lupin carried multiple roles at once: food, feed, soil repair, insurance. Soy specialized. Specialization brought efficiency, but it stripped systems of redundancy. That loss remained hidden until stress revealed it. Reintroducing Lupin does not mean returning to the past. It means applying old logic to new constraints. Modern tools can support resilient crops instead of overriding them. The future of agriculture is not primitive or futuristic. It is selective. It chooses which technologies serve biology and which replace it. Lupin fits into that future not as tradition, but as strategy. Every farmer faces the same question, whether consciously or not. How much control is enough, and how much resilience is necessary? Lupin shifts that balance. It trades some uniformity for forgiveness. It accepts variability in exchange for stability. In an era of uncertainty, that trade becomes rational. The crops that return first are not the most productive. They are the most reliable. Lupin was replaced because agriculture chose a system that no longer needed it. Now that system shows cracks. Protein crops that cooperate with soil, tolerate limits, and reduce dependency regain value. Lupin never stopped working. We stopped needing what it offered, temporarily. The question is not whether Lupin belongs again. It is whether we are ready to value what it provides.